To do this, I think I want to begin where I did with the piecewise function that we looked at last time, and just observe that since f of x equals x, if x is greater than or equal to 0, and negative x if x is less than 0, we can define f prime on the open interval from 0 to positive infinity, and on the open interval from negative infinity to 0, as being the derivatives of these expressions, and these are linear expressions. So we really don't have to work too hard to come up with the derivatives of these linear expressions. F prime of x equals something if x is greater than 0, something else if x is less than 0, and if x is equal to 0, that's going to be left for us to figure out. So if x is greater than 0, the slope of the tangent line is going to be the slope of this piece of the graph, which is what? 1. The slope of the line y equals x is 1. If x is less than 0, the value of the derivative is going to be the slope of this piece of the graph, which is negative 1. The slope of y equals negative x is negative 1. So negative 1. But I can't just get the derivative at 0 because 0 is not inside of either one of these open intervals. It's not in the open interval from 0 to positive infinity or from negative infinity to 0. It's an endpoint. So we have to do it like this. If it exists, f prime of 0 would be the limit as delta x approaches 0 of f of 0 plus delta x minus f of 0 all over delta x. That's the definition of derivative if it exists, if the limit exists. And what we'll see is that it's not going to exist. So to evaluate this, I'm going to simplify a little bit, and then we'll see that we need to consider the two one-sided limits as delta x approaches 0 from the left and as delta x approaches 0 from the right. So let's see, the limit as delta x approaches 0 of, f of 0 plus delta x, let's go ahead and say that's the absolute value of delta x minus the absolute value of 0 over delta x. The absolute value of 0 is 0, certainly. So maybe just say the limit as delta x approaches 0 of the absolute value of delta x, absolute value of delta x over delta x. Now, to evaluate the absolute value of delta x, we have to know, is delta x positive or is delta x negative? If delta x is positive, then it's just delta x. But if delta x is negative, it's not delta x because the absolute value can't be negative. It's got to be the opposite of delta x. So to figure this out, we consider the limit of the absolute value of delta x over delta x as delta x approaches 0 from the left, and the limit of absolute value of delta x over delta x as delta x approaches 0 from the right. To evaluate this limit, if they both exist and are equal, we'll declare the two-sided limit to be equal to their common value. If they both exist but are not equal, then the two-sided limit will fail to exist. Now, if delta x is a little bit less than 0, then it's negative. And the absolute value of a negative number is the opposite of that negative number. So this equals the limit as delta x approaches 0 from the left of the negative of, the opposite of, I should say, delta x over delta x. have to know if delta x is positive or negative before I can remove the absolute value bars. But now that we know it's negative, we can remove the absolute value bars and write it. So this is the limit as delta x approaches 0 from the left of -1, and the limit of a constant is that constant. So -1. Over here, this equals the limit as delta x approaches 0 from the right. Now, delta x is a little bit to the right of 0, so it's positive. So the absolute value of a positive number is just that number. So we lose the absolute value bars and write delta x. So this is the limit as delta x approaches 0 from the right of +1, which is +1. So the two one-sided limits both exist, but they don't equal the same number. So the two-sided limit, let's go with a capital D, capital N, capital E, it does not exist. So we have the graph of the absolute value function. Let's consider alongside that, or below that, the graph of its derivative. A very helpful exercise, I think, to see the connection between the graph of a function and the graph of its derivative is just to look at the graph, not so much the expression defining the function, but look at the graph and see if we can graph the derivative, the function that tells us the slope at any point. Well, it's going to be undefined at 0, but if we pick any positive number, the slope all along here, slope is 1, the 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 slope is 1. So it's going to be 1 all the way to the right. This is f of x equals the absolute value of x, and this is y equals f prime of x. Pick a negative number. I want to know what's the value of the derivative. Well, you look at the graph of the function. The slope is -1. Whoops, the slope is -1, -1, -1, -1, -1, -1. So it's constantly equal to -1. And hopefully this jives with what we just did in evaluating these two one-sided limits. If we look at this expression, if we're trying to evaluate absolute value of delta x over delta x as x approaches 0 from the left, it ends up being the limit of -1. X is approaching 0 from the left, and we get -1. If we approach from the right, we get +1. So the two don't meet. They miss each other like that, and so the two-sided limit does not exist there. So it's not differentiable at 0, even though it's continuous at 0. And what the takeaway from this is that when we're looking at a graph and there's a sharp edge, if we've got a graph that looks like this, and then something like, it doesn't have to be a right angle, but it can be just a corner, something like that. I don't know, you might not cut yourself on that, maybe it's not all that sharp, but it goes from being a certain value to being another value, and it misses the values in between. Right there at that point. So it's not a continuous transition from one value, the slope from one value to the next. And as far as the graph is concerned, the graph is not smooth. If it's got an edge to it like that, then it's not going to be differentiable. So this is a point of non-differentiability, if I can spell it. And other examples would be a cusp, something like that. It's not going to be differentiable right there at that point. Now, there are cases when the graph itself could be smooth, and I think example 8, were we to do it, I think actually could give us something that looks like this. If we have y equals the cube root of x, I believe the graph does something like this, something like that. And actually, the slope of the tangent line is undefined at 0. And it's what's called a point of vertical tangency. And if the slope is undefined, then the derivative is undefined, because the derivative is the slope of the tangent line. So that's another situation where it's a point of non-differentiability. So if there's a corner, it's not differentiable there. If there's a cusp, if there's a vertical tangent line, even though the function itself may be continuous, the derivative may not exist at that point. I think that's kind of the takeaway from an example like this.